In the last few lectures, we were considering unsteady unidirectional transport, okay, and we had derived general equations for mass, momentum and energy. They had the following form, where phi f v is the field variable, d is the diffusivity and s is the source. And these three have different are different for mass, momentum and energy transport, but the equations are both the same. Okay. And for the particular case where the diffusivity is a constant, you get this equation. Okay. And we had first applied it for steady, no sources or sinks. Okay. And there we had got a formulation in terms of the resistance. The field variable, the temperature or the concentration or the velocity fields, and there are steady state, no sources or sinks, all of them are linear functions of position. Okay. And you can combine the resistances in different forms, in the series form or the parallel form, where the series configuration is where the transport rate is a constant, but the temperature difference across each of those materials changes, whereas the parallel form is where the temperature difference across each material is the same, but the fluxes through each one are different. Okay. So, these were the different forms that we had solved. The next complexity that we had considered was the case where there is a source which is a constant. An example of this was viscous heating in a channel, okay, where we apply a constant temperature on both sides. The fluid is being driven by a relative velocity between the two surfaces, okay, viscosity mu, thermal conductivity k. Okay. In this case, the velocity profile is linear because there is no source or momentum source in the momentum equation. There is a source in the temperature equation due to viscous heating, and that is given by the product of the stress and the strain rate. Okay. And for a linear velocity profile, we had got this expression for the product of the stress and the strain rate. And if that is a constant, you can see that the second derivative of the temperature is related to the source. Okay. So, therefore, the temperature has to be a quadratic function, okay, of the cross stream distance. We had solved this to find out what is the temperature profile. Temperature profile is a parabolic profile. Okay. If the wall temperatures are the same, the temperature profile is a parabolic profile with a maximum at the center. Okay. The flux is a linear profile. Okay. So, we had solved this to get the temperature profile and the heat flux. The heat flux, heat is generated internally. So, at the center the heat flux will be 0 because of symmetry, and in the upper half heat that is generated will be conducted out through the upper wall. Lower half heat that is generated will be conducted out through the lower wall. Therefore, heat flux is positive in the upper half, negative in the lower half, and it varies linearly with position. Okay. And we had got the total heat transfer rate, and from that we had calculated an expression for the Brinkman number. Okay. So, now we will consider another example of transport due to a source or a sink, okay, and that is flow down an inclined plane, okay, inclined at an angle theta to the horizontal. Okay. And because of gravitational acceleration, I will have the flow down the plane. Okay. The gravitational acceleration is g. Okay. The acceleration along the flow direction will be g sin theta. Okay. If the plane is inclined at an angle theta to the horizontal, then the angle between the vertical and the perpendicular to the plane will be theta. Okay. So, the component of the acceleration perpendicular to the plane is going to be equal to g cos theta. The component of the acceleration along the plane is going to be g sin theta. Okay. So, that when the plane is horizontal, theta is equal to 0 and there is no component along the plane. If it is vertical, theta is pi by 2, g sin theta is 1. So, the gravitational acceleration is perpendicular is along the plane, okay, if it is vertical. So, the component of the acceleration in the flow direction is g sin theta. Okay. So, what is the expression for the momentum balance? Okay. At steady state in the presence of a gravitational acceleration. Okay. The momentum balance equation is d tau x z by dz plus rho g sin theta equal to 0. Okay. That is the momentum balance equation in terms of the shear stress. Okay. Note that there is no negative sign in front of the shear stress, because shear stress is effectively the negative of the flux. Okay. If I were to write this for mass transport, for example, I will get minus partial j z by partial z plus s is equal to 0. Okay. There is a negative sign here. In this case, for the momentum transport, there is no negative sign. Okay. Also note that in these equations I have used the total derivative. Okay. That is because it is at steady state and therefore there is no time dependence. So, the dependence is only on one variable and therefore we can use a total derivative. Okay. We can integrate this equation one time and get tau x z is equal to minus rho g sin theta into z plus a constant. Okay. How do we determine the constant? Okay. So, this is a film that is flowing down a surface. You have a solid surface here, there is a gas and there is a liquid. Okay. The constant, so I will take this as the z coordinate, this as the z coordinate and the flow direction as the x coordinate. The base is at z is equal to 0 and the top surface is at z is equal to h. Okay. So, this is the coordinate system. Okay. How do we determine the constant in the expression for the shear stress? Okay. Recall that at the liquid gas surface there can be a slip velocity, but the shear stress has to go to 0 at a liquid gas interface. Okay. Therefore, the boundary condition for the stress, note that this is a first order equation for stress. So, the boundary condition okay, tau x z is equal to 0 at z is equal to h. Okay. That is the boundary condition for the shear stress at a liquid gas interface. The shear stress has to go to 0, the velocity is non-zero at that surface. Okay. So, therefore, we can impose this boundary condition and get an expression for the shear stress as tau x z is equal to rho g sin theta into h minus z. Okay. The constant is rho g h sin theta. So, that the stress is equal to 0 at z is equal to h. Therefore, this is rho g sin theta into h minus z is the equation. Note that in this case I am first finding out the flux, because the source is a constant. Okay. How do I find the velocity? That will be calculated from the Newton's law of viscosity, okay, which is that mu dvx by dz is equal to tau x z. Okay, so, that is the Newton's law of viscosity. Okay. So, therefore, I can get Vx is equal to rho g sin theta by mu into hz minus h square by 2 plus a constant. I am sorry, z square by 2. if I integrate h minus z, I will get hz minus z square by 2. Okay. The constant is determined from the condition at z is equal to 0, okay, at the base. Okay. At z is equal to 0, the base, okay, the solid base, okay, you have to apply the no slip condition, okay, Vx is equal to 0 at the solid base, okay, which implies that C is equal to 0. Okay. Therefore, the velocity can be written as Vx is equal to rho g sin theta by mu into hz minus z square by 2. Okay. This factor, it is conventionally written hz minus z square by 2 is conventionally written as h square by 2 minus h minus z the whole square by 2. Okay. You can expand this and you will get h square by 2 minus h square by 2 plus hz minus z square by 2. Okay. So, yeah. Okay. So, therefore, the velocity Vx can be written as rho g sin theta into h square minus h minus z the whole square divided by 2 mu. So, this is a parabolic profile which has a maximum at z is equal to h and it is 0 at z is equal to 0. Okay. It is equal to 0 at z is equal to 0 and it has a maximum at z is equal to h. Okay. So, this is the parabolic velocity profile. Okay. It has a maximum at z is equal to h. Okay. It is 0 at z is equal to 0 because when z is equal to 0 this velocity is just equal to 0 and it has a maximum at z is equal to h. Okay. Yeah. Okay. Because d Vx by dz will be equal to 0 at z is equal to h. Okay. d Vx by dz here, okay, will be 0 at z is equal to h. And note also that the shear stress actually increases linearly with distance from the base. Okay. If I plot the shear stress, it is actually increasing linearly. Okay. It is equal to 0 at the surface and it is equal to a maximum at the base, that is it is equal to rho g sin theta at the base and is equal to 0 at the upper surface. Okay. Okay. So, now that we have this, we can now calculate what is the velocity. Okay. Maximum velocity mistake here. Vx at z is equal to h, okay, is going to be equal to rho g sin theta h square by 2 mu, because at z is equal to h this term is equal to 0. Okay. Therefore, I can write the velocity alternatively as V max is equal to, I am sorry, V is equal to V max into 1 minus 1 minus z by h the whole square. Okay. So, this is a parabolic profile. What is the average velocity? Okay. V average is equal to 1 over h integral 0 to h dz times Vx. That is, I take the integral of the velocity over the entire height h and divide by h to get what is the average velocity. Okay. And you can do this calculation. So, you will get this is equal to V max by h. Okay. So, let me write in terms of rho g sin theta. This integral. Okay. And you can calculate this integral and you will get rho g sin theta into h square by 3 mu. Okay. Rho g sin theta h square by 3 mu. Okay. You can verify this. Okay. The integral of h square is just h square z. So, that this gives you h cubed. And if I integrate these two terms, okay, hz minus z square, if I integrate these two terms, hz minus z square by 2, okay, hz will give me hz square by 2 minus z cubed by 6. So, I will get 1 by 2 minus 1 by 6, that is 1 by 3. Okay. So, that is the reason you get a factor of 1 by 3 by carrying out this integral. This implies that V max is equal to 3 by 2 V average. Okay. In this case, the maximum velocity is 3 by 2 times the average velocity. Okay. You can get an expression for the Froude number from this. Recall that the Froude number is the ratio of inertial and gravitational effects. Okay. V average by root G h. Okay. So, this is equal to sin theta by 3, I am just rewriting it in a familiar form. Okay. Rho square g h cubed by mu square whole power half. This, as you recall, when we did dimensional analysis, rho square g h cubed by mu square, this was the Archimedes number, okay, the ratio of gravitational and viscous forces. Okay. So, that was the Archimedes number. So, we get a correlation for the Froude number as a function of the Archimedes number to the half, okay, sin theta by 3. The constant is sin theta by 3. Okay. So, that is the solution for the Froude number for this flow down an inclined plane. The velocity profile is parabolic. Okay. Now, let us look at a slightly more complicated example, okay, and that is for so far we have considered cases where the diffusivity is a constant. Okay. So, in this case I had first derived for you the equation for the stress and then integrated that to get the equation for the velocity field. Okay. What happens for down inclined plane? Note that we had earlier written down the constitutive relation for a power law fluid, as tau x z is equal to mu dvx by dz power n, okay, when we did dimensional analysis. Okay. I am sorry, it should be k, okay, where k is the flow consistency index. And n is the power law index. Okay. So, what happens if we have this kind of a flow down the inclined plane? Okay. In this case, the relation between the stress and the velocity gradient is not linear. It is a more complicated relationship. Okay. The relation between the stress and the velocity gradient is no longer linear. It is a more complicated, a power relationship. Therefore, as the velocity gradient varies, the stress will also vary. Okay. And we consider the same problem, same configuration, flow down an inclined plane between z is equal to 0, z is equal to h at an angle theta, okay, flowing down. The velocity profile now will no longer be a parabolic profile. What will be the shape of the velocity profile in this case? Okay, so, let us examine that. So, this is a problem where the diffusivity is varying. In particular, the diffusion coefficient depends upon the strain rate. Okay. Even though the diffusion coefficient depends upon the strain rate, the equation between the stress and the gravitational acceleration is still the same. Okay. The relation between the stress and the gravitational acceleration is still the same. Okay. Momentum conservation equation written in terms of the stress is d tau x z by dz plus rho g sin theta is equal to 0. The boundary condition for the stress is the same, tau x z is equal to 0 at z is equal to h, which means that the solution for the stress is still the same, tau x z is equal to rho g sin theta into h minus z. Okay. So, when expressed in terms of the stress, the solution is exactly the same. You have a linearly varying stress, okay, with distance down. Okay. The relationship between the stress and the velocity is now different. Okay. I have k dvx by dz power n is equal to rho g sin theta into h minus z. Okay. Therefore, dvx by dz is equal to rho g sin theta by k power 1 by n into h minus z power 1 by n. Now, we can integrate this one time. Okay. We can integrate this one time. Vx is equal to rho g sin theta by k power 1 by n, okay, into some constant minus h minus z power 1 by n. Sorry. Okay, negative sign because I am integrating h minus z, which is the negative of the integral of z, and integral of a number a variable power 1 by n is that variable power n plus 1 by n or 1 plus 1 by n. Okay. At z is equal to 0, the velocity is equal to 0, no slip condition at the bottom surface. Okay. At the bottom surface, I have a no slip condition. The shear stress is 0 at the top surface. That condition has already been implemented when I got this expression for the shear stress. Now, I have to get the expression for the velocity. Okay. Using the boundary condition, no slip at the bottom, z is equal to 0. Therefore, Vx becomes equal to rho g sin theta by k whole power 1 by n into h power n plus 1 by n minus h minus z power n plus 1 by n. Okay. So, this is the velocity profile for a power law fluid. Okay. Recall that this reduces to the same that we had earlier if n is equal to 1 and k is equal to mu, because in this case the exponent of rho g sin theta will just be 1 and the exponent of h will be 2, which was the relation that we had earlier. Okay. So, this is the velocity profile. Okay. I am sorry, I should have, when I integrate it, I should have a factor of n by n plus 1. Okay. Integral dx of x power n is equal to x power 1 by n into x power 1 by n is equal to x power 1 by n plus 1 by, okay, is equal to x power n plus 1 by n into n by n plus 1. Okay, so, I should add this factor of n by n plus 1 here. Okay. So, that is the velocity profile. Okay. So, it has h power n plus 1 by n minus h minus z power n plus 1 by n. Okay. The maximum velocity V max is equal to V x at z is equal to h. Okay. At z is equal to h, this factor h minus z becomes 0 and this is equal to n by n plus 1 rho g sin theta by k power 1 by n h power n plus 1 by n. Okay. Alternatively, I can write V max as n by n plus 1 into rho g sin theta h power n plus 1 by k power 1 by n. Okay, so, that is the maximum velocity. Okay. What about the average velocity? Okay. This is going to be equal to n by n plus 1 that is the average velocity. Okay. 1 over h times the integral dz times Vx. Okay. So, I can simplify this 1 by h, sorry, okay. The first term is just a constant h power n plus 1 by n into z minus integral of h minus z power n plus 1 by n. Okay. This is going to be equal to n plus 1 by n plus 1, okay, divided by and this is going to have a positive sign because when I integrate h minus z I get plus, okay, it's the negative of the integral with respect to z. Okay. this is between 0 and h. Okay. Plus, okay. At h this is equal to 0, whereas at 0 this will be equal to, okay. So, at plus 0 minus h bar 2n plus 1 by n by 2n plus 1 by n. Okay. And you can simplify this, okay. The final result that I will just give you the final result, you will get n by 2n plus 1 okay, into rho g sin theta by k power 1 by n into h bar n plus 1 by n. Okay. This h 1 h will cancel out with h bar 2 n plus 1 by n to give you just h bar n plus 1 by n. So, this gives you n by 2 n plus 1 into rho g sin theta h bar n plus 1 by k. Okay. So, this is just some simple algebra which finally gives you the final result for the average velocity. Okay. And you can see that the maximum velocity is n by n plus 1 times this factor, and the average velocity is n by 2 n plus 1 times the same factor. Okay. So, the ratio of maximum and average is going to be equal to n plus 1 by 2 n plus 1. Okay. Okay. So, this is a calculation of the flow down an inclined plane both for a Newtonian fluid and a power law fluid. Newtonian fluid, source is a constant and the diffusivity is also a constant. You get a quadratic equation which gives you a parabolic profile. Power law, source is a constant, so stress is still a linear function of position. However, the relation between stress and the strain rate is not linear, and because of that you get a more complicated profile for velocity profile which has this particular form, okay. And from that I can calculate the average velocity and so on. The maximum and the average velocity both are proportional to the thickness power n plus 1 by n. For a Newtonian fluid it is proportional to thickness square for a given density, gravitational acceleration, viscosity, etc. So, I will briefly summarize this and then I will go on to the next topic in the next lecture. I will see you then.